Inside pretty much every server humming away in a data center, there's a secret. It's a hidden secondary computer that's always on, always watching, even when the main machine is completely powered off. Today, we're going to tell its story. So, picture this. It's the classic sysadmin nightmare, right? A server just drops offline. It's not responding to pings, SSH is totally dead, and the operating system has crashed so hard it took the whole machine with it. How in the world do you get control of a machine that you can't even turn on remotely? Well, the answer is you use the other computer. This computer within a computer, it's got its own processor, its own memory, even its own network connection, and it's built for just one purpose: to give you total, absolute control over the hardware, no matter what the main system is doing. And it's called the Intelligent Platform Management Interface, or IPMI for short. So here's our game plan. We're going to start by really digging into the core problem IPMI was built to solve. Then we'll meet the brain of the operation, the BMC, and see how everything connects. After that, we're doing a technical deep dive into its network security, which is super important. And finally, we'll talk about why this tech, which is kind of old, is still so critical today. Okay, so let's frame the problem. We're all used to managing computers through their operating systems, right? We use tools like SSH or remote desktop. But what happens when the OS isn't even running? It's crashed, it's frozen during boot, or the machine is just off. That's called in-band management. And when it fails, you're pretty much stuck. Unless, that is, you have an out-of-band solution. This is the key that lets us manage thousands of servers without ever having to physically touch them. And that is exactly what IPMI is. It's not a product, it's a specification, a blueprint that defines a standard way to manage computer hardware directly. The most important word on this slide is independent. IPMI works even if the system is powered down. It's a lifeline that sits below everything else for when all that other software fails you. So how does this magic actually work? Well, let's meet the central component, the real heart of the whole IPMI architecture. At the core of every IPMI system, there's a chip called the Baseboard Management Controller, or the BMC. Honestly, you can just think of it as the dedicated little CEO of platform management. It's a small, low-power chip that lives on the motherboard, and its one and only job is to run the IPMI firmware and give you that out-of-band access. And believe me, this little chip has a ton of responsibilities. We're talking way more than just turning the power on and off. The BMC keeps track of all the hardware sensors, it runs a watchdog timer that can automatically reboot the server if the OS freezes up, and it logs every major hardware event to a system event log, kind of like a plane's black box. It can even tell you the exact part number of a stick of RAM without you ever having to open the case. Pretty incredible. Now, a powerful brain isn't much good if it can't talk to anything. So let's take a look at the architecture and see how the BMC actually communicates with the server and, the rest of the world. The whole architecture is a classic hub-and-spoke model. The BMC is right there in the center, and it communicates using a standardized message-based protocol. And here's the really clever part. The same command, like get me the fan speed, can be sent from the server's own OS over a system bus, or it can come from a remote admin over the network. The command itself is identical, just the delivery method changes. And this just shows you how flexible the spec really is. To talk with the main system, the IPMI standard defines multiple ways to do it. Some, like KCS, are super simple. They basically pretend to be an ancient keyboard controller that every system has. Others, like block transfer, are way more modern and efficient. This variety is what ensures IPMI can be implemented on all sorts of different hardware. All right, the most powerful way to use IPMI is over the network. It's what lets you manage a server in a data center halfway around the world. But as you can imagine, sending power control commands over the internet brings up a massive question: security. So let's get into the technical nitty-gritty of how IPMI version 2.0 tackled this head-on. So the original IPMI v1.5, its security was pretty basic. The server would challenge the client would respond with a password hash, and that was about it. It worked, but it was definitely vulnerable. IPMI v2.0 was a huge leap forward. It introduced a symmetric challenge response, where both sides challenge each other. This proves that both the client and the server are who they say they are. Plus, it added stronger algorithms and much more robust session management. And all of this enhanced security is delivered through a protocol called RMCP+, which stands for Remote Management Control Protocol Plus. Think of this as the secure wrapper for all IPMI v2.0 traffic that goes over the network. It's the part of the spec that defines how to set up a secure session, how to encrypt the data, and how to carry different payloads. That means you can run more than just standard commands, like a full serial console, all over that one secure connection. So how does that secure session actually start? It uses a 4-step handshake called RAAKP, which is kind of like a mutual secret knock. First, the remote console starts things off by sending a challenge to the server. That's message 1. Second, the server proves it got it by responding, but critically, it issues its own challenge back. That's message 2. Third, the console answers the server's challenge in message 3. And finally, with both sides now sure of each other's identity, the server sends message 4 to confirm everything's good. Only then is that secure out-of-band channel actually open for business. Now, the first IPMI spec came out way back in 1998. In the tech world, that's practically ancient history. So why are we still talking about it? Because the problem it solves is fundamental. It's the technology that enabled the whole shift to massive, lights-out data centers, where a human physically touching a server is the absolute last resort. Because this is what it gives you. The power to reboot a dead machine from your living room. The ability to check a server's temperature before it has a chance to overheat. The power to read the error logs to figure out exactly why it crashed. The magic of getting a command prompt on a machine with no working OS, and the ability to get the serial number of a failed part without ever leaving your chair. This is the superpower of out-of-band management. And the reason it's been around so long really comes down to this one core philosophy, stated right in the spec itself. IPMI didn't tell companies how to build their management controllers, it just told them how those controllers had to talk to each other. This freedom allowed for all sorts of innovation and competition while making sure that the tools used to manage everything could be universal. Absolutely brilliant. And that brings us to one final thought. IPMI was really designed for the monolithic servers of the past. But today's data centers, they're moving towards these disaggregated systems. You've got separate pools of processors, memory, and storage. So in a world where the very idea of a server is being redefined, the core principles of out-of-band management are evolving into newer standards, like the Redfish API. The fundamental problem is still the same, but the interface is changing once again to meet it.